So we're starting a unit on combinatorics. This is chapter 6 in your book. Combinatorics is the mathematics of counting things. Um, Really, by counting things, we mean determining the cardinality of sets. So if I have some set that's described in a particular way, can I figure out how many elements are in that set? On the face of it, this actually sounds kind of boring and easy, but it turns out to be a surprisingly deep and rich area of mathematics with a lot of connections to other areas as well. It's honestly one of my favorite areas of mathematics. So it's quite possible, quite likely, that you memorized a bunch of formulas related to combinatorics in high school. So things like permutations and combinations, if that kind of rings a bell. So there are actually a bunch of fundamental principles on which combinatorics works. So my goal is to teach you those principles and teach you how to apply them, so that you could actually, instead of memorizing a bunch of formulas, you can just rederive the formulas if you needed to, that you understand where those formulas are coming from, and you can take those underlying principles and apply them in a bunch of different situations. So this isn't going to be about memorizing a bunch of formulas at all. So the first principle that I want to talk about, which is really one of the most fundamental ones, is called the product rule. And this is one of those things that when we state it, it seems pretty obvious, but the trick is finding ways to apply it, finding novel ways where it shows up. And the places that it shows up are not always obvious. So even though the principle itself seems pretty obvious, it definitely takes some practice to be able to apply it in a lot of situations. Okay, so the product rule says this. So suppose that choosing something choosing something can be decomposed into two independent choices. And I have C1 ways to make the first choice, and C2 ways to make the second choice. Okay, then the total number of ways to choose. I'll say total number of choices overall is C1 times C2. Okay. So a couple things to say. Number one, I'm often going to use this language of choosing things. So the number of elements of a set is the same as the number of ways to choose an element in that set. Your book also uses some kind of active language where it talks about performing some tasks or something. Somehow I find it helpful to use this sort of active language, like we are doing something, we're making some choices, as opposed to just saying, how many elements are in this set, which they're the same on some level, but somehow psychologically it seems easier to think about us actively making choices and thinking about how many ways we have to make those choices. So I'm going to use that language, but really fundamentally we're talking about figuring out how many things are in a certain set by asking how many ways we could choose something in that set. Okay? The other thing to say is, what does this independent mean? And that's important because we'll see some examples later. So independent here means that I have these two choices, right? And they don't change would I phrase this? Right. Or I'll say, you have the same set of options for both choices. Same sets. No, let me phrase it this way. The sets of choices don't change based on the other choice. Okay, so in other words, let's say that I'm picking a day of the week, and I'm also picking, let's say how many books I want to read on that day. And if they're independent, if I can pick a day of the week and I can also pick a number of books to read, and it doesn't, which day of the week I pick, it doesn't affect how many books I can choose. But if there was a rule that said, on Thursdays you have to read at least 2 books, but any other day you can read, 0 to 5, right? Then those are no longer independent because my choice of day affects which choices are available to me for the other thing. We'll see some more examples of that. But the point is that if the choices are independent, we can visualize it like this. So if the choices are independent, we can visualize all the choices in a sort of grid, right? So my first choice corresponds to what row I pick, and my second choice corresponds to what column I pick. And each of these squares corresponds to, a particular combination of the first choice and the second choice. And if they're independent, it means, for any row, I have all the columns available and vice versa, and so I get this nice rectangle. And obviously the number of squares, each square representing, one overall choice, is just C1 times C2. So that's where this comes from. And in fact, we've seen this before, right? This is really about Cartesian product of sets, right? So if I have a set A times B, it's a Cartesian product, right? It's like all possible pairs of A and B. That's the same thing as talking about, choosing an A, and I get to independently choose a B. And so the total number of things is going to be the product of those sizes. Okay, I think that's all I want to say about the product rule. So in the next video, I'm going to go through a ton of examples using this. Some are going to be straightforward, and then we're going to get into some other examples that are not quite as straightforward, but they all use the same basic principle.